Greetings and welcome to Distillate. Today, before we start with material balance, let's go through a very interesting unit of pressure. All right. So far, we have discussed a few units of pressure that include Pascal, which is the SI unit of pressure, which is also known as Newton per meter square. All right. Then we have ATM. So 1 ATM is basically 101325 Pascal, right? Then we have bar, which is 10 to the power 5 Pascal. Then we had mercury, which means that we have 760 millimeters of mercury is equal to 1 ATM. And then we studied torr, and 1 torr is equal to 1 millimeter of mercury, right? That's what we discussed, right? So now, apart from these units, let's come to a very interesting unit of pressure. So this unit of pressure is known as kg per meter square. It's actually kgf per meter square, but most of the places you will find it written as kg per meter square. So kgf per meter square basically means kg force per meter square. All right, this is the meaning of this unit. So let's understand how does this unit make sense? What is the meaning of this unit? So let's try to understand. So see, 1 kgf per meter square is basically the force that is exerted by 1 kg of a block. Force that is exerted by 1 kg of a block over an area of 1 meter square. All right. Again, 1 kg force per meter square is the force exerted by 1 kg of mass or 1 kg of a block over 1 meter square of area. All right. So what is force exerted by 1 kg of a block? Mass into acceleration due to gravity, mg. That's the force that is exerted by 1 kg of a block, right? So it's mass into gravity. So that is 1 into 9.81. Unit m is in kg, 9.81 is in meter per second square. So kg meter per second square is nothing but Newton. So this is 9.81 Newton. All right. And if we divide this by area, then we get it as 9.81 Newton per meter square or 9.81 Pascal. All right. So in short, what I'm trying to say is that 1 kg force per meter square is equal to G Pascal, or 1 kg force per meter square is equal to 9.81 Pascal. Hence, if you need to convert anything from Pascal to kg force per meter square, then we'll have to divide 9.81. All right, we'll have to divide 9.81. And if we have to convert something from kg force per meter square to Pascal, then we'll have to multiply 9.8. All right. So this was another unit that has been added to your list of units for pressure. So we have Pascal, we have ATM, we have bar, we have millimeters of mercury, we have torr. We also studied about kilopascal, which is actually 10 to the power minus 3, right? So Pascal, whatever you have in Pascal, it is multiplied by 10 to the power minus 3 to get kilopascal, right? So that's there. And after that, we finally have this new unit, which is 1 kg force per meter square, which is equivalent to 9.81 Pascal. So you should not forget the logic behind this unit. This is the force exerted by 1 kg of block over 1 meter square of area. Similarly, if I say 9 kgf per meter square, so that means this is the force exerted by 9 kg of a block over an area of 1 meter square. All right. So since now we are done with this unit, so let's again resume with our material balance. So the last class we studied about drying. All right. In the last class, we studied about drying. So we discussed that in case of drying, we have a dryer in which we send wet solid and we get dried solid from this dryer. All right. This dry solid may still contain moisture, but the amount of moisture in this dry solid would be lesser than what was present in wet solid. All right. Now, this whatever moisture will be lost by this wet solid, that is gained by dry air. Since in a dryer, what we do is we send dry air to dry the wet solid. So what happens? This wet solid, it comes in contact with this dry air and it loses its moisture to this dry air. Hence, this becomes wet air. All right, this becomes wet air. So we get water lost by dry solid. Sorry, not by dry solid. Water lost by solids is equal to whatever is the weight of wet solid minus whatever is the weight of dry solid. All right. Water lost by solids is equal to water gained by air, right? Whatever water is lost by the solids, that is gained by air. And water gained by air is equal to the mass or molar flow rate of wet air minus mass or molar flow rate of dry air. All right. So hope you people are clear with this thing. Then one more thing that I told you was to make your calculations slightly easier. What you do is you form equation for dry solid balance first. The first equation that you form is of dry solid balance. So if you form an equation for dry solid balance, that would actually give you one of the two. Either it would give you the feed flow rate or it would give you the product flow rate in most cases. In most cases, one of the two would be given. All right. Or at least you will get a proper relation between the two. So it would be easier to solve the problem if you form this equation first. Then one very important thing that I told you about drying, which is different from other unit operations, is that in drying, since solid is dominant, therefore we have the mole fraction or mass fraction of solute that we give, that xf and xp that we take, that is basically over here, this is taken for water. All right. Over here, this is taken for water. So this xf would be mole or mass fraction of water in the wet solid. Similarly, xp is going to be the mole or mass fraction of water in the dry solid. All right. So this was another thing that I told you about drying. So this is how drying is different from the rest of the unit operations. All right. In the rest of the unit operations, you generally have water as solvent, right? But over here, you have solid as the solvent. All right. Solid is the dominant phase. All right. So therefore, xf, xp, whatever we are going to take, that is going to be for water. All right. So once we are clear with this, then we move on to the next set of unit operations. So before that, let's once again revise crystallization. So this is a problem for crystallization that I have given over here. So go ahead, pause the video and try to solve this problem yourself. Hope you could solve this problem yourself. If you could not, then let's have a quick look at how to solve this problem. So whenever we have a crystallization problem, we have a crystallizer we have a crystallizer. All right. Then the feed, they have given that 700 kg of water is evaporated. I mean, okay. So for example, let's say F is the feed that is going in, feed solution that is going in. Then XF is the solute molar mass fraction over here. Then we have E as the water lost. XE is 0, of course. Then this is an anhydrous crystal, right? It is just K2Cr2O7, no hydrated condition, right? So that is why we'll get C, whatever it is, and we'll get XC as 1 over here, right? And then we'll have L, which is the mother liquor, and XL, that is the amount of solute in this mother liquor. All right, so that's how we are going to do. So information that is given over here is that a solution of potassium dichromate in water contains 0.15 K2Cr2O7. So XF is given to be 0.15. All right. Now this has to be used to produce 1500 kg of solution. 1500 kg of solution. All right. Oh, just a minute. Sorry. That can be produced from 1500 kg. So this is not 1500. This is not 1500. They have given that this 1500 kg is the solution. So calculate the amount of K2Cr2O7 that can be produced from 1500 kg of solution. All right, so that is 1500 kg is the feed, and 700 kg of water has got evaporated. All right, 700 kg of water has got evaporated, and they have also given the solubility. The solubility of K2Cr2O7 at 293 Kelvin, which is, when the remaining solution is cooled at 293 Kelvin. So this over here, mother liquor, it leaves at 293 Kelvin. Right, so obviously it's going to be saturated solution. So solubility over here is given to be 115 kg per 1000 kg of water. All right, so first thing we have to calculate XL. So XL is basically 115 upon 1000 plus 115, right? This is mass of the solvent, mass of the solute, mass of the solvent plus mass of the solute. All right, that is 115 upon 1115, right? That is your XL. So from here we get XL is equal to 0.103. All right, let's go and write this on in the block diagram. All right, so once we have XL, we have XC, we have XE, we have XF, we have F, we have E. So we can simply form our material balance equation. The first equation is going to be for overall material balance, which is F is equal to E plus C plus L. We have F, we have E. So we'll get L plus C is equal to F minus E. L plus C is equal to 1500 minus 700. That is 800. Equation number 1. Then let's do a component balance or solid balance. Right? So when we do solid balance, then we'll have XF into F is equal to XE into E plus XL into L plus XC into C. So this is 0. This is 1. So we'll have 0.15 into 1500 is equal to XL is 0.103 L plus C. All right, this is equation number 2. So on solving these two equations, we'll get L as 641.025 kg, while you'll get C as 158.975 kg. All right, so you've got F, you have got L, and you've got C. So determine the amount of K2Cr2O7 can be produced. So you have the crystal weight, right? So that's your crystallization problem. So hope you people could recollect whatever we had done in crystallization. And if you could not solve this problem, then please go back to the crystallization video and try to revise that topic once again. All right. Now we move on to today's unit operation, which is one of the last unit operations left. So that's absorption. Now this is a very important unit operation again. So what happens in absorption? We take a gaseous mixture of A and B. All right. A gaseous mixture of A and B is taken. In this gaseous mixture, we have one which is inert. All right, one which is inert. I'll get to that. All right, so this is fed to the absorption unit, and we also feed a solvent to this absorption unit. All right, we also feed a solvent to this absorption unit. So the solvent is selected such that it has affinity. Affinity means it has liking towards one particular component among these two. So let's say it has liking towards A. So it will try to take A. It will try to take A away from it. All right, away from the mixture. So what basically happens is when this gaseous mixture and the solvent, they come in contact. So solvent, it takes A away from this mixture, and this A, it gets dissolved in the solvent. And B is generally taken such that it is either not at all soluble in this solvent, or very small fraction of B gets dissolved in the solvent. Rest of it is not there. All right. So after this, towards the end, we have A plus solvent plus if some B has been absorbed, then B as well. Usually very less amount of B is there in this part. All right. And over here, from the other stream, we have lean gas. So lean gas basically contains B in majority, which is also known as the inert gas, the gas that is not soluble, or which is very less soluble in solvent, or the gas towards which solvent does not have affinity, does not have liking. That gas is known as the inert gas in absorption. So we have inert gas and let's say a very small percentage of A. Okay, a very small percentage of A that is remaining in this gaseous mixture. Rest of the A is absorbed by the solvent. All right. So that's how you use this process. So this process is generally in industry, it is used to remove or recover a particular component. So it can be either used to remove A from the remaining components, or it can be used to recover A from the remaining components. All right. So for example, this is generally used in carbon dioxide manufacture or acetylene gas manufacture and many others. Right. It's very commonly used process in industry. All right. So hope you people have got the concept behind absorption. All right. There's a solvent which has affinity towards one of the gases in the mixture, in a gaseous mixture. The other gas towards which solvent does not have affinity, does not have liking, is known as the inert gas. So when the gaseous mixture and the solvent, they come in contact, what happens? The solvent, it takes away A, or A, it gets dissolved into the solvent, and very less amount of A is remaining in the gaseous mixture. So the gaseous mixture with majority of B and very less or mainly no amount of A, maybe no amount of A, it comes out as lean gas, and the solvent A, and if some amount of B has been dissolved, then that it comes out from the second stream. All right. So this process is used to remove or recover a particular component from a mixture of gases. All right. So once we are done with that, so let's come to example number 1. Gaseous mixture containing 15% A and 85% inerts. That is, okay, let's not call it B because we have taken B as the solvent. Okay, no problem. So we have a gaseous mixture that contains 15% A and 85% inerts. Let's call it I. All right, so we'll call it as I. It is fed to an absorption tower where it is contacted with liquid solvent B, which absorbs A. So it has affinity towards A. The mole ratio of solvent to gas entering is 2:1. All right, that means 2 moles of solvent for every 1 mole of gas entering, right? For every 1 mole of gas entering, 2 moles of solvent enter. All right. The gas leaving absorber contains 2.5% A, 1.5% B. Some amount of B has been uh, all right, some amount of B has gone into gaseous phase. That is also possible. Sometimes the solvent, it gets vaporized, slightly vaporized, so you get some amount of solvent in this lean gas mixture. So while leaving the absorber, the gas contains 2.5% A, 1.5% B, and the rest are my inerts. All right. Calculate the percentage recovery of solute, the fraction of solvent fed to the tar, lost in a gas leaving the tar. So let's go ahead and form our block diagram first. So when we form the block diagram, remember, for absorption unit, whenever we have to form a block diagram, we have our gaseous mixture. All right. Then we have our solvent. Then we have our lean gas. And we have whatever the remaining solvent plus A. All right. Whatever is there. Right. So that's how we have things over here. All right. So now they have given us information about gaseous mixture. They have said that it contains 15% A and 85% inerts. All right. While B is the only solvent that is present. All right. So, okay. Then they have said that the gas leaving the absorber, it contains 2.5% A, 1.5% B, and the rest inerts. So 2.5% A, this is solvent is B. All right. 1.5% B and rest inerts. So what is the amount of inerts that would be here? 100 minus 2.5 minus 1.5, that is 96% inerts. All right. So this is basically our block diagram. All right. Let's take the gaseous mixture as G. Let's take the solvent as S. Let's take the lean gas mixture as L. And let's take the solvent plus A. Let's take it as anything. Let's take it as P. All right. So when we have this with us, so we'll start solving this problem. So they have not given anything about G or S. They have just given that the mole ratio of gas entering of solvent to gas entering. So solvent by gas, S by G is 2:1. Right? That is what they have given here in the problem. So what we are going to take, we are going to assume, or we are going to take a basis that one of them we'll assume. All right. So let's assume that basis, what we are going to take is that 100 kilomole of gas mixture enters the absorption unit. All right. So that means you have G is equal to 100 kilomole. So whatever quantities you are going to calculate, that is on the basis of 100 kilomoles per 100 kilomole of gaseous mixture. Although you are not needing any of the quantities per 100 kilomole because it's all fraction or percentage, so it's not that much of an issue. Okay, this 100 kilomole will somewhere or the other get cancelled. It just we have taken it for convenience of our calculations. All right. So we have taken basis as 100 kilomole of gaseous mixture that enters the absorption unit. So we have got G as 100 kilomoles. So S would be 2 into 100. That is going to be 200 kilomole. All right. That is going to be our S. All right. Now, what we are going to do, we are going to find L. All right. So just understand over here, as I told you, we'll try to take balance that particular component first, which has or which is present in lesser number of streams. Correct. So if we take A, so A is present in this stream, A is present in this stream, A is present in this stream. If we take solvent B, B is present here, B is present here, B is present here. If we take inerts, then inerts are present in this stream and this stream only. There has been nothing mentioned that inerts have been present over here. Inerts have been absorbed by the solvent. They have only given that solvent evaporates and goes to the gas, but they have not given that the inerts are soluble or inerts are dissolved by dissolved inside the solvent. So we are going to say that there is no inerts have been dissolved in the solvent. If we are going to take that condition, then we are going to do inert balance. All right. So inert balance would give us, there are 85% of inerts over here. So 0.85 into G is equal to. Now there are 96% inerts over here in the lean gas mixture. So that is 0.96 into L. 0.96 L. All right. So we have 0.85 into 100 upon 0.96. That gives us the liquid gas mixture. All right. That gives us the liquid gas mixture. No, that gives us lean gas. Sorry, not liquid gas, lean gas. So L is equal to 85 upon 0.96. That is 88.54 kilomole. All right, 88.54 kilomole. That is L, or the lean gas mixture. All right. So once we have this thing, then we can we know G, that is 100. We know S, that is 200. And we now also know L, that is 88.54. All right. So now we can form the overall material balance equation. So when we do that, so when we form the overall material balance equation, we get S plus G is equal to L plus P. So S plus G is equal to L plus P. Right. So 300 minus 88.54 is P. So from here you'll get P as 211.46 kilometers. All right, 211.46 kilometers. All right, so that's P, 211.46 kilometers. So we have found P as well, that is 211.46 kilometers. Now, once we have almost completed the block diagram, so let's go back. So we have to see the percentage recovery of solute A. So percentage recovery is given by A in solvent, that is A that has been absorbed, upon A in gas mixture. All right, that is the A that was fed. All right, so A absorbed upon A fed, right? So A absorbed is going to be whatever A is present in the solvent. So let's say XA is the mole fraction of A in the solvent. So we'll get XA into XA into P upon A fed is 0.15 into 100. That is 15, right? Into 100. Okay, into 100. Okay, so now we have to calculate A. So what we are going to do, we are going to balance A now, right? So let's do A balance. So when we balance A balance, right? So when we balance A, we'll get now A is present in this stream, and in this stream. So we'll get 15, that is 0.15 into 100, that is the input A, is equal to 0.025 into L plus, let's call XA over here. So XA into P. So L and P we have already calculated, right? So from here, you'll get XA as 15 minus 0.025 into L. L is 88.54 upon P, which is 211.46. So when you calculate, so you'll get this approximately as 0.06. So XA is approximately 0.06. So when we substitute it over here, so 0.06 into P, that is 211.46 upon 15 into 100. So that gives you 84.584. 84.584%. All right. Okay. So once we have calculated this, then we go back. So the percentage recovery of solute A, we have calculated. Now we have to calculate the fraction of solvent B fed to the tar lost in gas leaving the tar. So basically what we have to see is that the B that is lost here upon B that was fed here, right? B that is lost here upon B that is fed here. So B over here it was pure B and over here it's 0.015. So we are going to take fraction of B lost is equal to B in lean gas, right? Because that's not where it's supposed to be, upon B fed into 100, right? So that is 0.015 L, right? This is 1.5%. So 0.015 L upon B in feed is 200, right? Into 100, right? In percentage. So that is 0.015 L, we calculated it as 88.54. So into 88.54 upon 200 into 100. So this is equal to 0.0075%. Okay. This is the percentage of B that has been lost in lean gas. All right. Remaining whatever B was there, it was recovered. It has been we have got that B. Only this much percentage of B has been lost. So hope you people could solve this problem. All right. So now we move on to the next problem. Go ahead, pause the video and try to solve this problem yourself. Hope you could solve this problem. If you could not, then let's have a look on how to solve this problem. So it is given that acetone is recovered from an acetone air mixture containing 25% by volume acetone by scrubbing with water. This is volume percent, so this is same as mole percent, right? So yeah, assuming that air is insoluble in water, determine the percentage of acetone in the entering gas that is absorbed if gas leaving the scrubber analyzes 5% acetone. All right. So basically what you have to calculate is percentage of acetone that has been absorbed. So that means acetone in solvent upon acetone in feed. That is what you need to calculate, right? So let's go ahead. First of all, we'll draw a block diagram. So we have our absorption unit. All right. Then let's take M as the mixture. All right. So we have M as our mixture of acetone and air. So this mixture, it contains 25% acetone. That means it contains 75% air. And there is water, right? There is water that is coming in as solvent. So let's call it S simply, that is water. Now, since air is insoluble in water, so all the air would be present here, right, in the lean gas. Okay. In the lean gas, all the air would be present. So air would be here and it contains 5% acetone as well, right? It contains 5% acetone as well. And again, there has been no information given about water being vaporized, right? There has been no information given about water being vaporized. So we are going to take this as 95% air. All right. That is what we are going to take. We are going to assume that there has been no water that has been vaporized. All right. Although this is not quite needed. All right. Then over here we have the solute, that is acetone, solute gas, acetone plus water, right? That is what we have over here, right? So now let's start our calculations. So again, there has no information been given about MSL or let's call it P, right? So MLS or P, they have not given any information. So we are going to again take the basis and solve the problem. So basis is that we have 100 kilomole of acetone air mixture. So M. So basically M is 100 kilomole, right? So that is why if we have 100 kilomole of mixture M, then that means we have 25 kilomole acetone, right? And 75 kilomole is going to be air. All right. 25 kilomole is acetone and 75 kilomole is air. All right. So now what we are going to do, we are going to do air balance. All right. So let's go for air balance. So that is where you will be using this particular 95%, right? So 0.95 into L is equal to air that is present here, which is 75 kilomole, right? So L is going to be 75 upon 0.95. All right, 75 upon 0.95, that is 78.95 kilomole. All right, that is your L. Lean gas is 78.95. All right, this we have taken as 100 kilomole. All right, once we are done with that, then we are going to see, since we have got L, so obviously we'll get acetone in the leaving gas. All right, so acetone in lean gas is going to be what? Since it has 5% acetone, so 0.05 into L. So 0.05 into 78.95. Right. So that is going to be equal to whatever the acetone that is present, that is 3.95 kilomole. That is the acetone present in the lean gas. So acetone absorbed. What is the acetone absorbed? That is equal to acetone fed minus acetone in lean gas. Right? Whatever is acetone fed minus acetone in the lean gas. So acetone fed is how much? 25 kilomole, right? Acetone fed is 25 kilomole. So 25 minus acetone in lean gas is 3.95 kilomole, right? So yeah, so it is going to be 25 minus 3.95 kilomole. So since it was given that acetone is 25 kilomole in the entering gas and 3.95 kilomole, we just calculated that is acetone in the leaving gas, right? Okay, so this is equal to 21.05 kilomole. This is the acetone absorbed. All right. So now we have to calculate the acetone in solvent upon acetone in feed. So this is the acetone that has been absorbed. So this is equal to basically acetone in solvent. Whatever is the acetone absorbed, that is equal to acetone in solvent. And acetone in feed, we just saw it was 25 kilomole of acetone. So we get percentage acetone absorbed is equal to acetone in solvent, that is 21.05 upon acetone in feed, that is 25 into 100. So that is going to be 84.2%, right? 84.2%. That is the acetone that has been absorbed. All right. There is nothing much that you need to worry. All right. If suppose they would have asked you about P and S, then how would you have proceeded? So since you have acetone here, you have acetone here, you would have done acetone balance, and you have also got the acetone that has been absorbed, that is here, right? So based on that, you would have done acetone balance. All right. And then you could have also formed the overall material balance equation. M plus S is equal to L plus P. All right. M plus S is equal to L plus P. And then you could have calculated P and S. All right. However, you might be needing some more information for this calculation. For example, you might need the molar ratio, M by S or S by M. All right. Anyhow, now we move on to the next unit operation. It's quite similar to it's quite similar to absorption. And this unit operation is basically extraction. So what is extraction? Extraction is whenever we have the absorption, it is same as absorption. Just in absorption, what we took here, A plus B, that was the gaseous mixture, right? Over here, we take it as the liquid mixture. All right. We take it as the liquid mixture. So now this absorption unit, it becomes the extraction unit. All right. It becomes the extraction unit. It's the same thing. All right. So again, separated by a suitable solvent. So the phase which is rich in A, all right, which is rich in A after separation, the phase which is rich in A is known as the extract phase. All right. While the phase which is rich in B is called the raffinate phase. All right. The phase which is rich in A is called the extract phase, while the phase which is rich in B, that is the inert, or you can say the component towards which the solvent does not have enough affinity. So we are going to take that, the component which, the phase which is written, that component, that is known as the raffinate phase. So two phases, one is extract phase, the other is the raffinate phase. So it is again used to remove or recover a particular component liquid. All right, a particular component liquid from a mixture of liquids. All right, from a mixture of liquids. Okay, so that is what is your extraction unit. All right. So once we have understood the extraction unit, it has to be done the same way as we did absorption. So let's go ahead with example number 3. A mixture containing 70% chloroform and 30% acetone. Let's call chloroform. All right, let's not give any names. All right. So it is extracted with a mixed solvent containing acetic acid and water. All right. Now solvent is also mixed, and acetone and chloroform, of course. Right. So let's call it as A. Chloroform, let's call it as B. Acetic acid, let's call it as S1, and water, let's call it as S2. The two immiscible phases, the raffinate phase and the extract phase, have the following composition. And the basis is that we have 100 kg of mixture to be extracted. So you have to determine the following. All right. So since we have 100 kg of the mixture, all right, we have 100 kg of mixture that has been extracted. So that means extract phase contains 100 kg. Extract phase is basically 100 kg. Right. So that is why we have So we'll be having the block diagram. So this is our extraction unit. All right. So there will be mixture of the mixed liquid that would be here. So let's call it F1. So over here you have acetone as how much? 30%. And chloroform that we took as B, it is given to be 70%. Right? Then the mixed solvent over here is, it contains let's call it F2, and it contains S1 and S2. We are not sure what these values are. All right. Then we have the extract phase. Let's call it E. So the extract phase, it contains 0.7% acetone. So acetone is 7%. It contains B. It contains S1. It contains S2. Even the raffinate phase, it contains all the four. All right. So it contains A, B, S1 and S2. All right. So once we have these things, so let's see. 7% chloroform is 3%. So it's 3%. S1 is going to be how much? 30%, and water is going to be 60%. So this is 60%. Then for the raffinate phase, you have 20, 67, 10, 3. 20. Sorry. Oh, this is the raffinate. So 20, 67, 10, 3. Right? So that's the case. Right? Now they have given for the basis of 100 kg of mix. I think I told you people that this would be extract. Basis is 100 kg of the mixture extracted. So mixture extracted is this, the feed solution, right? This is the mixture that has to be extracted, right? So that is why F1 they have asked us to take it as basis 100 kg. Although it doesn't really affect, because even if we take basis over here, anything, if we take E as the basis as well, then also it's going to be the same result. S1 and S2, they are going to become the same. But yeah, of course, the values are going to change. E, R, F2, they will be changed. So that is why let's go with the question, right? So F1, they have asked us to take it as 100 kg. So this is all the information that is given to us about this problem, right? So now it's quite easy. Try to avoid the use of this stream as much as possible, because here we neither know F2 nor we know S1 and S2. So if possible, avoid the use of this stream, all right, because it would give you complicated equation. All right, so A and B are not present in this stream, right? So we are going to do the first equation for A balance and the second equation for B balance. So let's balance A. So A balance, the equation is 0. 0.3 into F1, that is A in the feed, is equal to 0.07 E, that is A in the extract, right? Extract phase, plus 0.2 into R, right? So F1 is 100, so basically you'll get 0.07 E plus 0.2 R is equal to 30. That is your equation number 1. All right, then let's balance B. All right, let's balance B. So when we do that, we'll get 70, right? 70 in the inlet, 70 over 0.7 into 100, 70 is equal to B in the extract, that is 0.03 E, plus B in the raffinate phase, that is 0.67 R. So you will get 0.03 E plus 0.67 R. This is equal to 70. This is your equation number 2. All right. So once we have got these two equations, there are two variables, two equations. So we can solve for E and R. So when we solve, we have E equals to 149.144 kg and we have R as 97.8 kg. So let's go ahead and write it over here. E is 149.144 kg, right? And R is 97.8 kg. All right. So now since we have E, we have R, we have F1, therefore we can simply find out F2. So we are going to do overall material balance. So an overall material balance gives you input F1 plus F2 is equal to output, that is E plus R. Therefore, your F2 is going to be equal to E plus R minus F1. All right. So F2 is equal to 146. So your F2 is going to be equal to 146.944. All right. It's basically 149.144 plus 97.8 minus 100. Right. So that is going to be 146.94 kg. Right. So once we have this information with us, therefore we can go and write it over here, 146.944 kg. All right. So once we have this, then we can use this stream as well for a material balance. So we've already formed overall balance equation and A balance and B balance. Therefore, let's go ahead and form one equation for S1 balance. All right. So let's say S1 over here, the fraction of S1 is, let's say X1. All right. So let's say we are taking X1 as the mass fraction of S1 over here and X2 as the mass fraction of S2 over here. All right. So we will get X1 into F2, that is S1 in the inlet, is equal to 0.3 into E, S1 in the outlet extract phase, plus 0.1 into R, that is S1 in the raffinate phase, right? 0.3 into E plus 0.1 into R, right? So when we solve, we already have E as 97.8 kg. No, we have R as 97.8 kg. We have E as 149.144 kg. And we have F2 as 146.944 kg. Therefore, on solving, we get X1 as 0.371. All right. So therefore, X2 is going to be 1 minus 0.371. That is equal to 0.629. All right. So we have 37.1% of S1 and 62.9% of S2. So now this block diagram is complete. Now let's go to the question and see what they have asked. The composition of the mixed solvent on weight basis. So this is the composition, 37.1% acetic acid and 62.9% water. Next, they have asked the quantities of extract and raffinate phase, so that we have calculated here. Extract phase is 149.144 kg and raffinate phase is 97.8 kg. And then third problem, they are asking the amount of mixed solvent used. So the amount of mixed solvent is F2, which we have calculated as 146.944 kg. So that's all. That's the end of this problem. So let's go on to example number 4. Go ahead, pause the video and try to solve this problem yourself. Hope you could solve this problem yourself. If you could not, then let's go ahead and see the solution. two liquids A and B are only partially miscible at a certain temperature. 59 kg of B and 41 kg of A are mixed well, and the mixture is allowed to settle. The mixture separates into two immiscible phases, one rich in A and the other rich in B. The A rich phase analyzes 90% A and the B rich phase analyzes 80% B. What are the weights of A rich and B rich phase? It's quite easy. It's just direct material balance. You have the extraction unit. Let's draw the block diagram. So you have the extraction unit, right? Then you have pure A coming in at that is 41 kg, and you have pure B coming in that is 59 kg, right? So A rich phase, let's call it E, and B rich phase, let's call it R, right? So A rich phase, it analyzes A as 90%, right? It analyzes A as 90%. And therefore B over here is going to be 10% only. And over here, B is analyzed to be 80%. This implies that A is going to be 20%, right? So once you have done this, then we are going to form A balance equation. It's actually quite easy. You can directly just form material balance and A balance. So A balance equation is going to be 41, that is A in the inlet, is equal to 0.9 into E, that is A in the A rich phase, plus 0.2 into R, that is A in the B rich phase. So this is your equation number 1, and then you can form the overall material balance equation. So outlet E plus R is equal to inlet 41 plus 59. So that is E plus R is equal to 100. That is your equation number 2. So when you solve equation number 1 and 2, you will get E as 30 kg, and you will get you will get R as 70 kg. All right, E is 30 kg and R is 70 kg. So that's what you have to calculate, weights of A rich and B rich phases. So A rich phase is 30 kg and B rich phase is 70 kg. All right, so hope you could solve this problem easily. Now we come on to the last problem of this lecture. A 100 kg mixture containing 28% acetone, which is A, and 72% chloroform, which is B by weight. It is to be batch extracted at 300 Kelvin with a mixed solvent consisting of water S1 and acetic acid S2. The mixture of the original feed solution and mixed solvent is shaken well, allowed to attain equilibrium, and separated into two layers. The composition of the two layers are given as follows. Upper layer, let's call it E, has this as the composition, and lower layer, let's call it R, has this as the composition. Calculate all these things. So first of all, go ahead, pause the video, and try to solve this problem yourself. Hope you could solve this problem yourself. If you could not, then let's have a look. So first of all, we are going to draw the block diagram for this problem. So this is my extraction unit. All right, this is my extraction unit. Now I have 100 kg of mixture that is entering the mixed solvent. So 100 kg mixture, let it enter from here. It contains A and B. A is 28% and B is 72%. So 28%, 72%, right? And then we have mixed solvent. So let's call it S. Or let's call it S, right? So it contains water and acetic acid. All right. So that is going to be S1 over here and S2 over here. That we don't know, right? Then from here it gets separated into the upper layer, which is E, and the lower layer, which is R. The composition of the upper and lower layer are given in the question. So we'll just write it down. So upper layer, they have given 7.5% A, 3.5% B. 3.5% B. Then we have 57.4% S1. And finally, 31.6% S2. Right? Then we have 20.3% A in the lower layer, 67.3% B. So that is 20.3% A, 67.3% B. Then 2.8% S1 and 9.6% S2. And 9.6% S2. Right? So that is your composition. So now you have to do material balance, basically. That's what you have to do. So once again, it's same as the example number 3 that we did. We are going to avoid this stream. All right. So we are going to form A balance and B balance equation. So first of all, let's follow the A balance equation. So the A balance equation is going to be 0.28 into 100 is equal to 0.075 E plus, that is E in the A in the upper layer, and 0.203 into R, that is A in the lower layer. So you get 0.075 E plus 0.203 R is equal to 28. That is your equation number 1. Then we are going to form B balance equation. So when we form the B balance equation, we get 0.72 into 100 is equal to 0.035 E, that is B in the upper layer, plus 0.673 R, that is B in the lower layer. So we get 0.035 E plus 0.673 R is equal to 72. That is your equation number 2. All right. So 0.035 E plus 0.673 L. 0.673 R is equal to 72. All right. So once we have got these two equations, hence we can find E and R since we have two equations and two variables. So E is equal to 97.486 kg, right? And R is equal to 101.914 kg. Right? E and R. Right? These are the two values we have got. E is 97. Let's put it here. 97.486 kg. And R is 101.914 kg. All right. So once we have got this, therefore we can form the overall material balance equation and get S. So we are going to form the overall material balance equation. So the overall material balance equation is 100 plus S, that is inlet, is equal to 97.486 plus 101.914. All right. So therefore, we get S as 99.4 kg. All right. You will get S as 99.4 kg. All right. So once we have this information, S. So this is what we have. Then again, let's assume X1 and X2 as the mole fraction, or mass fraction of S1 and S2 in S. So then we are going to form the S1 balance equation. All right. So we are going to form the S1 balance equation. So S1 balance equation is going to be X1 into S is equal to 0.574 into E. That is S1 and E. So 0.574 into E plus 0.028 into R. That is S1 in R. So from here, we get X1 is equal to 0.59. So accordingly, you'll get X2 as 0.41. So this is 59% and 41%, right? So you have 59% of S1 and 41% of S2, all right? So the quantities of the two layers, you have got E and R. Then the weight ratio of the mixed solvent to the original mixture. So the mixed solvent is 99.4 kg, original mixture is 100 kg. So the weight ratio is equal to 99.4 upon 100. That is 0.994, right? And then you have the composition of the mixed solvent by weight. So that is S1 and S2. So you are done with this as well. So hope you people could understand what these two unit operations were about. First unit operation was absorption. The second unit operation was extraction. So in absorption, the gas phase and solvent come in contact, and the solvent has affinity towards one of the gases, and that gas gets absorbed by the solvent, and we finally get lean gas and solvent, right, from the absorption unit. In the extraction unit, instead of gas phase, we have a liquid phase mixture. We have a liquid mixture, we have a liquid solvent, we come in contact with each other, and we get two phases, extract phase and raffinate phase. So extract phase is basically written A, and raffinate phase is written B. All right, so once we have all this, then we discussed about conditions where the solvent is a mixture of two different components. For example, acetone water or acetic acid and water. So if that is the case, then you don't touch the solvent stream. Instead, it is better to first balance the two components in the mixed liquid stream. That is component A and component B. Using that component A and component B, we first find the extract and the raffinate phase, and after that, using overall material balance, we find the solvent weight. And once we get that, then we can easily find the composition. So that is how you proceed with extraction unit operation. So that is the end of material balance without chemical reactions. From the next lecture, we're going to start with material balance with chemical reactions. So that is going to be another very complicated topic. So before we start that particular topic, you have to make sure that you're very clear with material balance without chemical reactions. You know how to balance different units. You know how to form mass balance equations. So just make sure that you are clear with whatever this topic is. You should be very clear about how to go with material balance without chemical reactions. So this is a self-assessment quiz kind of a thing. So it consists of 5 questions. All right, there are 5 questions in this particular quiz. So you people can attempt this particular quiz to check how much are you prepared. All right, and if you don't get a particular question right, then please go back and watch the video for that particular topic and then proceed with the further topics. Otherwise, this is going to be very complicated. Okay, the link for this quiz is provided in the description, so you people can definitely access it.